quite.
All right. So this was a short question here. Which of the following has the lowest resistance? Let's see. Conductors let the electricity through. That's the wire that goes through your extension cord. That's supposed to conduct electricity. Otherwise, your stuff on the end of the wire won't work. So this one has low resistance. It's probably this. Insulators are supposed to not conduct electricity. That's the rubber stuff that's on the outside of that what am I saying? Extension cord. And that has very high resistance so that you can grab it without the electricity coming through from the wire through the rubber part to your hand. So insulators have high resistance, conductors have low resistance, so that's the answer, conductors. All right, please go to this assignment for today. It says Magnetism 1. It's Wednesday, if you didn't know. All right. So there's questions on that assignment, on that Google form that go with this. If you're watching me do this right now, then you may want to have the PowerPoint available so that you don't miss anything, or so that, if you miss something, then you can go back. Or, you don't have to. But I've got a few versions of it attached. I've got the Google Slides version, the dark version, and the light version. This is the dark version. And then I've got the PowerPoint version, dark version, and light version attached. So hopefully those translate well when you try to open them on your devices. So I tried. Let me know if there's problems, and maybe I can do something. I'm not sure. Like a PDF of the thing, then maybe that'll work. But hopefully it just works. Anyway, this is a rock. You guys like rocks? This is a rock. The mineral Magnetite, in particular, that's what this is. It's iron. It's a dense rock, so if you have a big rock of it, this is probably pretty heavy. It's just iron, and it doesn't come as a magnet. It's just iron. It's called magnetite though because it can be magnetic, but when you find it, it's not normally magnetized already. However, some pieces of magnetite are found magnetized already. Scientists think that it's probably like it got struck by lightning, or lightning struck really nearby, and this is very important for what we're doing. Excuse me. Whenever there's electricity, there is a magnetic field. They always go together. So if you've got a lot of electricity, like lightning is a lot of electricity, it has a strong magnetic field next to it, and that strong magnetic field can turn these pieces of iron into magnets, like actually magnetized magnets. So that's what scientists think that lodestones are. Lodestones are magnetite that's found already magnetized. Somebody found one in the region of Magnesia in Greece long ago, and people also found them other places, and we think that maybe that's why magnets are called magnets, because of this region, Magnesia, but we don't really know. I think that's 2 questions, right? Lodestone question and magnesia question. Good? Can I go to the next slide? Like this? Okay. This is a compass. You got some ancient Chinese compasses here, 2,400 years ago. Pretty cool. Wow. No, not all these slides have questions. This slide does not have questions. This guy, only 600 years ago, used a compass on a boat. They had boats a long time ago, so I think they were probably using compasses before this. I don't really know. I'm not a history guy. That's the one subject that I don't really know about, history. I don't know. It's not my thing. This guy, we've heard this name before. We got the French physicist Charles Coulomb. We studied him. Thank you. We studied him when we had Coulomb's law with the charge. K, Q1, Q2 with the charges. So he studied electricity. He also studied magnetism because they always go together. You can't study one without studying the other. This is George West. Okay. So this guy is a physicist and chemist, Hans Christian Urstead. This is the letter Ö. It's a Norwegian letter, I think. Letter Ö. He discovered that electric currents create magnetic fields. So he's the first guy to discover why these two go together, I guess. Electric currents create magnetic fields. So if you got your phone plugged in, that's electric current going from the wall to your phone, making a magnetic field around that wire. Right? Okay. Magnetism is an example of a field force. This is the question. Field force. We got a bunch of different field forces. Let's see if we can name them all. 1, magnetism. 2, gravity. 3, electrostatic force. You know, you rub the balloon on yourself and that's a field force. 4, we got field forces inside an atom. The strong nuclear force and the weak nuclear force, keeping the quarks together, keeping the nucleus together. We'll learn more about that later. That's only 5. There's 2 more. I don't know what they are. We said gravity, right? I don't know. There's other field forces. Anybody can think of any?
Wait, what was the question?
What are field forces? Well, I'm asking you. The question that is on your sheet is, what kind of force is magnetism? It's a field force. Yeah, I'm not sure. Well, I don't want to waste time on that. I mean, it wouldn't be a waste. I want to know. Gravity. Yeah, we said gravity. Oh, man. Yeah, so the closer the magnets get, it's one of the things it says, the closer the magnets get, the stronger the force is. But we knew that, I think. Intensity of the interaction depends on the distance between magnetic fields. A magnet can act as a compass. Now I know, magnets have poles, so the north pole of the magnet and the south pole of the magnet. The end that points northward is called the north pole, the end that points southward is called the south pole. Seems real basic. The poles type thing and the way the compasses do gets a little weird here in a minute. So stay tuned. Aha, here's a riddle, and this is a question on your sheet. Excuse me. Sorry, video people. So, rule number 1. North poles and south poles can never be separated from each other on a magnet. Rule number 2. You can break a magnet in half. So, if you can break it in half right here, but a north pole can never be separated from a south pole, what does that mean will happen if you break a magnet in half?
The north pole will stay the north pole, but the side you broke off from will be the south pole.
The black hole.
It's like little tiny mini magnets inside of the bigger magnet.
I think that's probably.
Right? Something like that.
Probably. Answer the question, tell what you think will happen, and then we'll go on to the next slide. So yes, the answer is mini magnets, as you said. You break it, each half becomes a magnet. So it's like, you got all the particles pointed one way in here. The end of the particles are pointing away from is the north pole, the one that they're pointing toward is the south pole. And before, it went all the way through, but this is still the one they're pointing away from, and that's still the one they're pointed toward. The south pole is still the one they're pointed toward here, so you break it again, you'll have a north pole here and a south pole here, north pole here and a south pole here, because that's just the way everything's pointing. So that's why when you break it in half, you end up with little magnets.
What if you shatter it, make it little pieces? They all get little magnets.
I mean, they'll all be magnetic still. I've got some magnet, because magnets can be you get those little button magnets and neodymium magnets. If they break, and they can be pretty brittle too, so they can break pretty easy. And sometimes they can have magnetic force working against themselves in it, so they have some internal stress, and maybe that makes them easier to break. But
How do you make
if it shatters, you still get little magnets. They're still magnetic. They still have their poles point the same way. If you could put it back together, now that's another thing. If you hit a magnet, then it can take it out of. They can make it not be a magnet anymore. But we'll talk about that. We're talking about it. We're going to talk about it. Here's a question. Y'all might already know this, probably. Rules of magnetic poles interaction. The rules are: like poles repel and opposite poles attract. South and south repel. North and north repel. North and south attract. That's the way magnets work. I mean, that's what they do. We're going to learn actually what makes magnets do that magnet thing where they do attraction or repelling. But we're not there yet. We'll get there. Oh man, iron filings are scary, man. If we use these in class to make like these lines, then that would be the most dangerous thing that we do. I mean, we got things flying through the air sometimes, and we wear goggles for that. We definitely have to wear goggles for this, and we have to make sure we know where the eye wash is, because these things are very small and very pointy. And they're scary. I don't like iron filings. But anyway, we got iron filings. You can see they are following the magnetic field lines around this magnet. And they're just laying down on the paper because of gravity. If we were in space and you just took this magnet and just put it in space and then shook all these little iron filings around it, it would do this in 3 dimensions. It'd come out like this, out like this, out like this. Anyway, there are magnetic field lines, and you can see they're really close together up here, and you got a lot of iron filings attracted where they're really close together, because the magnetic field is stronger where they're close together. Magnetic field lines go in a particular direction. I don't know if I made a question out of this. I probably should, but what we got? They go out of the North Pole into the South Pole. And that's why the arrows point like that. So they go up and they go in. And you can see how close the lines are together, near to the poles. That's why the poles are the most magnetic place. They're the place that does the most magnetic force. The field strength is greater where the lines are closer together. I think that's a question on anything. Am I doing okay? Am I going too fast for y'all or anything? Okay. Okay. All right, so he's another scientist that we've heard about. You guys heard of Nikola Tesla?
Yes.
He's a guy. As far as we know, he was, there was the whole thing with Edison and the AC and the DC and whatever, and it's been a little bit more dramatized recently than it was in the day probably. But he studied electricity. Edison was doing light bulb stuff, and Tesla was doing electricity stuff. Electricity and magnetism are so interrelated that Nikola Tesla's name, is on the unit for magnetic field strength. It's Tesla with a capital T. If we say, the Earth's magnetic field is so many microtesla, that's what we would use. It'd be micro capital T. What we got? Charles Gauss is another French guy that did electricity and magnetism. That's why he's also associated with the magnetic field unit. He's not the SI unit. That's not the one that they decided on, surely way after these people were done studying this. But you guys ever, you know those old TVs that go way back behind the screen, the CRT TVs, not the flat screen ones? Those things, if you can mess those screens up by, if you put like a magnet next to the screen, or if they're like speakers. One of the reasons speakers are so heavy is you put the speaker next to those CRT screens. The speakers have a big magnet in them. That's part of why they're so heavy. Sorry. If you put that speaker right next to the screen, that magnet can mess up that screen. It can make it turn like green and purple when you're trying to watch, and it makes a big permanent green and purple spot on the screen. But hold on. If you go through the settings, you go, brightness, contrast. On those TVs, there's a setting for degaussing. You can go select degauss, and it'll like reset the magnetic field, I guess. And that's how you can relate this guy Gauss to real life. Guess what you got?
So is that like the same thing when you know how to give me the hotel card, you buy it, they say like get things to call it, is that the same thing?
That's probably related. If if your credit card stops working because your magnetic strip got interfered with somehow, that's probably the same sort of thing.
There's
Or
this thing where like,
hotel keys, gift cards.
yeah, if you put like the hotel key with like phone case or whatever, it'll like mess up your phone or the key itself or whatever.
Oh, huh? I don't know
I've
about
heard
that.
of that too.
What we got? Wait. Okay, so you remember those lines? They go from north to south. This is where compasses get interesting. So forget what you know about compasses. Magnetic field lines go from north to south. So this, if we were doing an arrow with a magnetic field line, it would go this way, and it'd point this way toward the south pole. It'd point this way. And then they go in right here. All the little arrows would be going here, pointed that way. So the question, it's a questionary thing. Make sure you answer it before we go on. What would happen if we place a compass in this magnetic field with these little lines that point this way? These letters are supposed to be green. I'm pretty sure. Anybody have it open? Are they green on your screen? They're yellow on the projector. Oh, y'all are doing the white version. That's okay. So they will line up with the field. The arrows point from north to south, and the compasses will point toward the south pole of the magnet. That's how it works on Earth, too. It says more on this later. That's on like slide 70 something. We'll be working on this for 3 or 4 days. Yep. Earth's geographic north geographic pole, is where Earth's south magnetic pole is. So they're named backward, and that's why compasses point toward what we think of as north. It's the north geographic pole. It's not the north magnetic pole. That's in Antarctica. The compasses point toward the south magnetic pole, which is located in Urstead, on the north geographic pole. It's weird. I think this is a question. Every electric charge is surrounded by a magnetic field if it's moving. So y'all, I think I've probably already said this, but it's real important. Y'all with your phones plugged into the wall or your laptops plugged into the wall, the electricity that's moving from the wall to your phone, that's got a magnetic field around it. And that applies to electrons too. I mean, that's what electricity is. Going from the wall to your phone to charge it is electrons. When they move, they make magnetic fields. And everything's got electrons in it, including magnets, but also including like wood and plastic and stuff that's not magnetic. So electrons are electric charges, and they do move. They move in any material. That's how magnets work, but it's not quite that simple. It's weird. So let's go find that. Ow. Oh, I got my messed up comma right here. Here, I'll fix it. I'll fix my comma. Okay. There, I fixed my comma. Are you ready? So this is a picture of what electrons actually do. It had a picture where it had like the little orbits of them, where it looks like it's got little moons orbiting a planet or something, a planet. That's not how electrons work. they just have a probability of existing within these areas, depending on what kind of atom it is. Or what kind of, you remember your S energy level, your P energy level, your D energy level from chemistry? That's what these are pictures of. The nucleus is in the center of each of these little pictures here, in the center of that sphere there. So electrons just have a probability of existing in that area because they don't exist like normal matter that we're used to. And when they move, they don't like go doo-doo-doo-doo-doo in circles. They like teleport around in there. It's a quantum thing and it's very weird. But it's not a whole orbit thing, that's fake. Anyway, they move around in there by teleporting, and that produces a magnetic field because they're moving. That's current because moving electrons that are teleporting around, that is current. So it makes a magnetic field. However, they also spin, and this is the important part. I think there's a question that asks what are the two ways they move inside the nucleus. They move around in the electron cloud, and they spin. So you can tell, will you get the lights, please? Just that one light, just, yeah. Ah! You can tell they're spinning here, and they're spinning as making a magnetic field. This one's spinning this way with a magnetic field that goes like this, and this one's spinning this way with a magnetic field that goes like this. So this is the way they make the stronger magnetic field. When they teleport around, that doesn't make a good magnetic field. The spinning one makes a strong magnetic field. So I've got a pair of electrons here, and one's spinning this way, one's spinning the other way. Y'all remember these little arrows from chemistry, where you filled out like one for the S level? Yeah. So this is a pair of electrons, and the arrows mean this one's spinning this way, this one's spinning this way. They are always paired up, electrons are, and they're always paired up with an oppositely spinning one. And that's important. Okay, you can turn the light back on. Thank you. All right, okay. So if they spin in the same direction near each other, they make up a stronger magnet because they're spinning in the same direction, their magnetic fields add up. They don't really do that because they're always paired with an oppositely spinning one. So what usually happens, electrons spinning in opposite directions cancel out their magnetic field. And in wood and plastic, which has electrons, and they're always in pairs, and they're always paired with the oppositely spinning one, and oppositely spinning ones cancel out each other's magnetic fields. That's happening in wood and plastic and all the elements that can't be made magnetic. They always cancel out their magnetic fields. All those oppositely spinning paired electrons. We're good? I think we're good. This is a question though. The three elements that can be magnetic, and there's other materials like steel has this stuff in it, and there's other materials that have this stuff in it, like alloys and stuff like that, of these things, when they're mixed with other metals. Anyway, the three elements that can be made magnetic are iron, nickel, and cobalt. And that's a question, make sure you answer. So each iron or nickel or cobalt atom is a tiny magnet. And now that doesn't mean the more atoms you have, the more magnetic it is, because they might be pointed different ways. The magnetic fields might be pointed different ways. The atoms themselves, not just the spinning electrons, but the whole atom. Ready?
No.
No. I don't know what's with this picture. It looks like that's all the same metal. It's just some shiny cylinders. Like, look, it's some metal. Pretend that this is iron, nickel, and cobalt. Ready now? All right. Okay, so those atoms aren't always lined up, but when they do line up, you get a cluster of lined up atoms where their magnetic fields are lined up. So clusters of magnetically aligned atoms are magnetic domains. You can see this is 20 micrometers. That's 20 million meters. micro's abbreviation is this little mu that we keep seeing. So this is 20 millionths of a meter. And all these atoms have their magnetic fields lined up. Magnetic domains are clusters of magnetically aligned atoms. That's a question. That's about what is the domain. So here's a bunch of those domains. These are all the domains is a group of aligned atoms. So all these atoms have their electrons, have their magnetic fields aligned, but they're not lined up with the group of atoms next to them. So each of these domains, they can be all jumbled up. This is a piece of iron that is not magnetic. So back to that lodestone magnetite thing. If you find magnetite, it's iron, but usually it's going to be like this. It's not going to be magnetized already unless you got struck by lightning and then it lined up all of its domains. Because lightning is a current. And wherever there's lots of current, there's a big old magnetic field. And that magnetic field can line up all these the same way that lightning's magnetic field is going. So when you do make a piece of iron or nickel or cobalt magnetic, you can put it in a magnetic field. That's one way, and there's another way we'll talk about in a minute. But if you put it in a big magnetic field, two things occur. So all those arrows in the last slide that are all next to each other but not pointed the same way, one of those arrows in this little group of arrows in one part of it ends up winning and convinces the other little domains next to it to turn its way. It's like, look, I'm the good one, turn my way. And so they all turn that way. And next door, this guy won, and all these start turning this way. And you end up with bigger domains. So the domains grew because in a certain area, one of the domains won, so to speak. But once they grow, there's more magnetic force going this way, and this one has magnetic force going this way, so they're all pulling on each other. And eventually, once they get big enough, they all pull. The pulling ends up, they end up, deciding to go one way, so to speak. They're not actually, alive. But so two things happen. The domains grow, and then they rotate to all to go the same way. If you put iron or nickel or cobalt in a magnetic field, domains grow and they rotate. I think that's a question. I had to make all new stuff for this. It used to be a piece of paper. I had to decide. It wasn't even a piece of paper that I made, so I had to decide. Everybody got their mask on out there? I'll have your mask. All right. So there's two ways. You can place that nickel or iron or cobalt, or the alloys that have that stuff in it, in strong magnetic fields, like that lightning does. That's the strong magnetic field to make that magnetite into a lodestone. Or you can stroke a piece of iron with a magnet. So if you take like a screwdriver and you put a magnet on it and just run it along the length of the screwdriver, you can make it so it'll pick up the screws. And so it'll be harder to drop the screw. Like you can put it on the end and turn it sideways and it'll stay on there while you're trying to screw something in. And so that's useful. So what that does is it aligns the domains, like those little arrows, it makes them all point the same way. That's a question. And then another question is, well, how do you make it unmagnetized? So you can heat it up, or you can hit it or drop it. When you heat it up, well, okay, so when you drop it, that kind of shakes all the atoms around, and it can make them turn around so they're not aligned anymore. And you drop your screwdriver enough times, you're going to have to re-magnetize it, which you could do. It's fine. It's not going to ever lose its ability to magnetize again, but just don't drop it, and then it won't knock the domains out of alignment. Or you can heat it up, and heating it up does really the same thing. When you heat something up, its atoms start shaking around more. That's all heat is kinetic energy of molecules. So that causes vibration of molecules also, and that will bring the domains out of alignment also. So 2 ways to break it. Heat it up or hit it. Not to break it, to bring the domains out of alignment so it's no longer a magnet. All right. Yeah, see, we got like, 5 more minutes or something. So, all right, we got moving electron produces a magnetic field. So this is a picture of the wire that goes from the wall to whatever you're using with your electricity or charging or whatever. If the electrons are going this way, the magnetic field around it will go in a particular direction, and we're gonna see how to do that. How to figure out what direction things are going. All right, so this is called the right-hand rule. If you put your thumb in the direction the electricity is going, so if you're grasping the cord that's coming away from the wall, make sure it's insulated so you don't electrocute yourself. Point your thumb in the direction of that cord, your fingers will show the direction of the magnetic field around it. In this case, it'll go that way. I want to see everybody's thumb. I'm going to come walk around and look at your thumbs. Pretend like you've got a wire like this coming straight out of your desk, going from the floor to the ceiling, and that's the way the electrons are going, from the floor to the ceiling. So point your thumb in the up direction. Make sure your thumb goes as straight up as your thumb does. I know not everybody's thumb will do everything. So let's turn the lights on so I can see your thumbs. Good. So, and then it will go that way. Cool. This is the right hand rule. This is going to be useful. You're going to have, when we take the test over this stuff, when I walk around like this, I'll take a test. I should see everybody be like, let's see, this way. Like looking like crazy people, making their hands go all sorts of ways, because you're going to have to figure out stuff using the right hand rule.
Wait, I'm so
on the test.
confused. What does this do?
This shows, so if you know the way that the current is going in the wire, that's point your thumb in that way, and your fingers will show the way the magnetic field curls around. So it'll say, okay, the current is coming out of the page. So if you're looking at the page, okay, I'll point my thumb with the current, and it'll say, okay, which way is the magnetic field going? And you're like, well, let's see. It's going counterclockwise. Counterclockwise, click. Huh? And we're going to do an example here.
So it shows the direction of the magnetic field in a straight line or in a curved path.
Well, your fingers are curled around, I
Okay,
guess.
in a curved-
So the current, if the current is straight, you point your thumb in the direction of the current, and then your fingers show the direction of the curly magnetic field. Yeah, the key word there, your fingers would curl around the wire. So for this question,
But for your thumb, it'd be obviously in a straight line.
yeah, your thumb goes straight with the current. But it's the right hand rule can do a little bit more than this, which we'll see later. Not today. All right, I think that's fine. That's fine. Yeah, we'll do an example with this tomorrow. I'll start on this slide tomorrow just to make sure everybody got there. And let's go to the closing activity after you make sure you got these questions answered.
Yeah, how do